Welcome to Compressible Flow 3. Our lesson objectives for today are going to be 1, to describe shock waves, 2, to calculate the flow properties downstream of a normal shock wave, and we're going to do that in the context of a problem for today. So we're going to spend most of the lesson talking about those flow properties and how to do some calculations in a problem. Calculate the location of a shock in a converging diverging nozzle is our third objective, and we'll look at some of those things that go with a shock in a nozzle as well inside a problem. First objective, I recommend that you do two things. Number one is read the textbook. The second is to watch this converging diverging rocket nozzle video that is posted on Blackboard. This video has a great discussion about what happens to the flow when we're subsonic or supersonic, and it's a nice visual depiction of the flow itself as it moves with those speeds and under those different pressures, and talks about pressures under several different conditions and how that produces either subsonic or supersonic flow, and then also discusses shock, which pertains particularly to the first lesson objective in our lesson today. So let's get into our problem so we can do some calculations. So what we have here is a converging diverging nozzle. See the shape. And we're going to consider the flow isentropic. That's one of our key assumptions that we've built on the previous compressible flow lessons. We'll treat our air as ideal gas with constant specific heats, and doing those two things will allow us to use the tables A18 and A19 in our reference manual. We'll make it easy on ourselves. We won't have to do interpolation. We'll just pick the closest value to make solving the problem faster and easier. We're given that the area where the shock occurs is going to be at 0.97 feet squared. We know for a shock to occur, we have to be supersonic. So that means we have to be somewhere beyond the throat where Mach 1 is. So we'll be somewhere to the right in our diverging nozzle with our shock right here. And that area is going to be 0.97 square feet. And we're asked to figure out the back pressure, or really the pressure at the exit of the nozzle here. We're given lots of good information about the inlet, so we know the stagnation pressure, stagnation temperature, stagnation density, the velocity and the speed of sound at the inlet, as well as the area at the inlet is 0.8 square feet. Okay, so let's take a look at our problem here. Let's kind of draw it out. This is a nice way to outline how to solve these problems, and I recommend when you get a converging diverging nozzle, you do something very similar to this and kind of sketch out your states and give you a path to solving the problem. So the first thing is we'll denote we've been told there's been a shock on the diverging part of the nozzle, so we'll draw that there. And we're going to define two states, states A and B. We're going to say state A is just prior to the shock, state B is just after the shock. Technically, the states A and B arrive or occur very close together. They're drawn here a little bit separated just to be able to draw the shock wave in the middle. A and B are very similar locations because a shock is when the flow properties change and the pressures change dramatically in a very short period. And that's what generates the shock, or that's what we call the shock. We have an inlet, of course, on the left-hand side. And we know that the flow, we've been told, is isentropic through the converging nozzle here, and that's going to continue to the center, or what we call the throat. And our throat has properties. We know that if we're subsonic in the converging nozzle, then we must be supersonic in the diverging nozzle. So that means right at the middle, that transition point, we'll have a Mach of 1. Our throat is denoted by that asterisk symbol. So we'll call that the throat. The state of the throat will be denoted by the asterisk. We'll have some area associated with the throat, some particular pressure associated with the throat. At state A and B, again, just a reminder, we're given this area, so it kind of tells us where in the cross section of this nozzle or diverging nozzle the shock occurs. Our flow leaves the throat from our throat state and moves to the pre-shock condition at state A. This again maintains and is still isentropic flow, similar to diverging nozzle that we had in previous lesson and material. To go from state A to B, so through the shock or after the shock, One of the key points that we need to take away from shock and understanding shocks is that when shocks occur, the flow is no longer isentropic. So this nice isentropic assumption that we had in the first, from the inlet to the throat and then from the throat to state A, we cannot make as we cross the shock from A to B, and that is a huge significant point that you need to understand for this material. This will generate our second table for us, table A19, to deal with that problem and to work around or work through that. Then we'll also denote that at the exit, we can go from state B to E and leave the exit. And there is no shock between B and E, so this is isentropic flow as well, and we can model it similar to the way we did in previous material. And we're asked again to find that exit pressure. All right, so let's just put our roadmap together so we have a strategy to solve this problem. The first thing we're going to do is we're going to take the flow in parts. So we're going to go from the inlet to the throat. And again, we denote it's isentropic. Because it's isentropic flow, we can remark that the stagnation pressure at the inlet, which we're given here as 40 psi, is constant because it's isentropic flow. So that means that the stagnation pressure at the throat we know is also 40. The next step is we're going to go from the throat to state A just prior to the shock. Again, this is isentropic flow that we have. And if it's isentropic flow, that means the stagnation pressure is the same. So between the throat and then at state A, the stagnation pressure remains the same, is unchanged. Those two ideas lead us to that the stagnation pressure at A is equal to the stagnation pressure at the inlet. In other words, we have stagnation pressure of 40 psi at the inlet, at the throat, and at state A. And that'll allow us to use table 18 because we're isentropic flow. So table 18 for both of those pieces. Step 3 is going to go across the shock. And so we need to flow from A to B. Again, this is not isentropic. That means that the stagnation pressure between A and B are different, and we will lose energy as we go from A to state B. We're not isentropic. So our flow is no longer reversible. Remember, a definition of isentropic flow is adiabatic and reversible. In this case, the shock is going to cause irreversibilities, and we will lose energy. Thus, the stagnation pressure is different. We'll use table 19 to help us jump across the shock, and that's where table 19 is handy. And then finally, state 4, we come back to an isentropic flow, but we're going to model the flow of the shock as essentially a new problem. And we'll talk about that, and I'll show you about that in a little bit, where we're going to kind of redraw our diagram to handle the flow after the shock because our stagnation pressure, once we get to state B, is different. So to go from B to the exit, we are still isentropic, although our starting point B does have a different stagnation pressure. Because we're isentropic, that new stagnation point at pressure at B is the same as the exit, or the exit is the same at B. And that's what we can denote there. Okay, so that's a nice discussion. So let's take this first step in hand. Remember, we're going to go from the inlet to the throat, and that is an isentropic process for us. Again, we talked about because we're isentropic, our stagnation pressures are going to be the same. So the inlet at the throat is really equal to just one stagnation pressure value, which we say is 40 psi because we know the inlet is 40. That's going to be very handy for us. We're given both the velocity and the speed of sound at state I, or at the inlet. So we can get the Mach number, velocity divided by the speed of sound. So we put those values in. Units cancel, and we're left with a Mach number of 0.64. So this is subsonic, although the Mach number definitely will indicate that we have compressibility effects. So we can note that down up top. Our Mach number is 0.64. With that Mach number, we can jump into table 18. And we're going to look at a couple of different lookups at table 18 because we want to understand what is going to happen at the throat. We have all the information given to us at state I, or at the inlet, but we need to understand some of the properties that are occurring at the throat, and so that's where Table 18 will help us calculate that. So Table 18 is going to relate the inlet to the throat properties for both area and pressure. We already know the Mach number at the throat, by definition, is going to be equal to 1. So let's jump into Table 18. So here is Table 18. Remember, Table 18 is for that isentropic flow piece. Ideal gas, constant specific heat. So we are meeting our conditions for Table 18. And we remember that our Mach number was 0.64 right here on our table. And we can pull two values out there. We can pull out the ratio of the area to the area at the throat. So this is the area at the inlet divided by the area at the throat. And then we can do the same with pressure. So we can record those values. So the area at the inlet divided by the area at the throat is 1.1451. And the pressure between the throat and stagnation pressure is going to be 0.7591. We can use the area ratio to calculate the area at the throat. We know it's going to be something less than the area at the inlet. And it's about 14% less, and so we come up with 0.8 square feet divided by 1.1451, which leaves us with a value of just under 0.7 square feet. So we record that up top because we're going to use that number later. That's going to be handy to get. We'll do the same idea with our pressure. We can calculate the static pressure at the throat, and that's going to be equal to about 76% of the stagnation pressure. We know the stagnation pressure is 40 psi, and so the calculation is pretty simple. It's going to be about 30.364 psi. And then again, that is the static pressure at the throat. So we'll list that here. Okay, so we've successfully moved to the throat, and we've calculated some properties at the throat. We could also get the temperature if we were interested in that. Step 2 is going to help us move from the throat to state A. So we're still remaining pre-shock, so we're isentropic flow. And we could denote that we know the area at state A is 0.97 square feet. That's a given for the problem statement. And if you remember, we just determined the area for our throat is just under 0.7 square feet. So we can put these two in a ratio. Feet square cancel out, and we get a ratio of 1.3885 between the area at A to the area at the throat. So that allows us to look into Table 18. So if we look at Table 18, we can see that 1.3385 lies somewhere between a Mach number of about 0.5 and 0.45, probably just under 0.5. It's pretty close to 0.5. We could effectively assume it's something about 0.5. We could also note that we see that same ratio of about 1.338 occur somewhere between 1.75 and 1.8 Mach numbers. So there's two Mach numbers. Remember, we discussed this last lesson. There are two solutions, a subsonic solution, so a Mach number less than 1, and then a supersonic solution, a Mach number greater than 1. So we can see that we'll have a Mach number of about 0.5 and 1.75, and we can record that here. This says 0.51. It's probably something actually about 0.49. Make a correction there on the chart. We know that the flow at A is going to be supersonic because we have to be supersonic to have a shock. So that means that we can reject the subsonic Mach number, and we can assume the Mach number is 1.75. And so we'll record the Mach number down here as 1.75, and that's at state A pre-shock. At a Mach number of 1.75, we could get some properties at state A. So we could get the ratio of the temperature at state A to the stagnation temperature. And remember, we're given stagnation temperature right here. And we could we could calculate the ratio of the pressure, static pressure at state A, with regards to the stagnation pressure, which is given right here, and we know that carries throughout all of the isentropic flows. So let's go to table 18. Let's look that up. So remember, our Mach number is 1.75. And we're going to calculate those two ratios. The pressure, static pressure to stagnation pressure gives us about a 0.1878 value. And then the static temperature to stagnation temperature gives us a value of about 0.6202. So we record those. And we can do some calculations. Let's solve for the temperature at state A. We get it's about 62% of the stagnation temperature. We know the stagnation temperature is 655 Rankine. So that gives us a static temperature at state A of about 406.23. So we see the temperature has dropped, and that makes sense to us. Our static temperature would drop as the flow begins to accelerate. We can use the pressure ratio we just found a minute ago to solve for the static pressure at state A, and it's 18 or 19% of our stagnation pressure, which we know is 40 psi. And we calculate that, and that we find that our static pressure at state A is significantly lower. It's a 7.5 psi, so we can record that up here as well. So we've learned a lot about state A. So our next step now is to move across that shock as we go from state A to state B. Remember that movement from A to B is across the shock, so it is not isentropic. We are an irreversible process. So we'll make a note that because it's an irreversible or non-isentropic process, the stagnation pressures between A and B are not the same. The stagnation pressure at B we expect to be lower. If you recall, we said that the Mach number at state A we knew was 1.75, so going into the shock, our Mach number is high, it's at 1.75, and we'd expect after the shock that the Mach number at state B will be significantly lower. We can look up a couple different ratios here. We can look up the ratio of stagnation pressure post-shock to pre-shock, B to A. We can look up the ratio of static pressure post-shock to pre-shock, and we can look up static temperature post-shock to pre-shock. And so let's look up those three values. Remember, our Mach number is going to be 1.75, and that'll give us three values here. Here's our temperature ratio listed at 1.495, pressure ratio at 3.406, and our stagnation pressure ratio is at 0.8346. So we have those values recorded, and now it's a matter of just calculating a few things. The stagnation pressure at B we can calculate is about 83% of the stagnation pressure at state A, which we found a minute ago. And we know it is 40 psi. And so that means the stagnation pressure at B is 33.384, and that drop from 40 psi to 33 psi represents basically an energy loss that occurs due to irreversibilities. And so we'll record that stagnation pressure up here, up top, for state B. The static pressure at state B is 3 times the static pressure at state A. That's expected because we know that we're going to come in at a high Mach number of about 1.75, and we're going to shock and drop the velocity or Mach number down significantly. And if we drop the velocity, we know from the stagnation pressure definition, if velocity drops, dynamic pressure goes down, so that means static pressure must go up, and it's going to go up by over almost 3.4 times as much. We know that our pressure we calculated a moment ago at state A, static pressure was about 7.5 psi. So that tells me that the static pressure at state B is going to be 25.586 psi. We'll record that here as well. Not required for the problem, but the temperatures are interesting to look at to learn what happens across the static temperature across a shock. And we can see that the ratio is something greater than 1, so that means that as we go across the shock, after the shock, the static temperature will go up. It goes up by almost 50%. And we know that our static temperature at state A, we had calculated that a minute ago, was about 406.2 Rankine. So 50% more than that gives us about 607.3 Rankine. And so that's where we can see the effects of the shock. So the static temperature is going to go up. We went from 406 Rankine to 607 Rankine. Because our flow is no longer isentropic between the shock or across the shock, we've lost stagnation pressure, and so we kind of need to reset the problem. So what we're going to do is we're going to essentially redraw the problem as a new nozzle problem where our stagnation pressure is lower because of the cause of the shock. And so we're going to imagine a subsonic diffuser in this case for us, and we'll talk about in a minute why we call it a diffuser in just a moment. Our point in B in our diverging shape has not changed, so that location is still the same. And we could actually even make a note here. We know the Mach number at point B. We can get that from table 19. Remember, at state A prior to the shock, we had a Mach number of 1.75. We can go to table 19 and we could look up and find the Mach number at point B, and I'll give you just a moment to look that up. All right, I hope you've had the chance to look it up in table 19. And we can see that if we go from a Mach number of 1.75, we shock down to a Mach number of 0.6281 across state B. We're going to redraw our throat now, and we can imagine what would a subsonic diffuser create? What throat would we need to create a Mach number at 0.62 at state B? So we're kind of imagine this new throat, and we're going to call this new throat. We're still going to note an asterisk to denote the throat, and we're going to use a subscript B just to denote that it's different than the throat that we were using for most of the problem in the beginning. Because it's a throat, we know that our Mach number is going to be 1 here, and we're going to call this the throat for our problem or for the flow of B when it's subsonic. So our flow is going to go from this new throat definition to state B. We also have an exit, and we're given that area at the exit. And the flow is going to go isentropically now because we're after the shock to from state B to the exit. And again, we're going to essentially, we've removed the shock, and we're just going to redo this problem as if it doesn't have a shock, but we're going to use the new stagnation pressure that was caused by the shock. And so that new stagnation pressure we're going to denote there, listed there. And if you recall that is 33.384 psi. Okay, now we're on track. We can complete step 4. We can go from after the shock to the exit. And we remember this is a isentropic model, but this is a new model where our stagnation pressure is lower than 40. Our Mach number at A, if you recall, was at 1.75, so that is still a handy value for us when we think about table 19. So let's jump into table 19. We want to look at the ratio of the area between A and B of the throats. So this is the area of the throat that we had once upon a time in our original design, and then this would be our imaginary. What would the new area of our imaginary throat need to be? So if we had a Mach number at 1.75, we can see that the ratio of the throat post-shock or aftershock to the pre-shock throat area is 1.1982. We're going to take that value, we'll put it here, and that's going to allow us to calculate the area of our imaginary or our new throat. And it's just a fraction, or it's something a little bit larger than the throat that we had previously at A. And so our new area of our throat is going to be 0.8371 feet squared. We could also denote or look at this that we know something about the area at the exit. We know 1.33, so we could look at the ratio of something we know or given to what we just calculated right here. We can rewrite this in terms of just the ratios for the exit. So this would be the area at the exit, 1.33, divided by the area at the throat for associated with the exit. And we could remark that we know that these two areas, the area at the throat for B and the area at the throat for E, are the same because we're working with the same model. So it's the same area. So 1.33 feet squared divided by 0.8371 feet squared. Units cancel, and that gives us a ratio of 1.5889. That's an area ratio that we could look up in a table. Because it's subsonic flow, let's go back to our subsonic table. That's table 18. And we could look for a Mach number. So let's go into table 18 and look that up. So with our area ratio of 1.588 and some change, we can look at the ratios and we can denote that the closest one on the area ratio is 1.59. So we could take that to avoid interpolation. We can read across here and we get some other values. But really what we're keying in on here is the Mach number of 0.4. So that means that as we bring it back here, the Mach number of our exit is at 0.4. So we can see that the flow is slowing down. So we have a Mach 1 of here at the throat, in our imaginary throat, a Mach number for real of 0.6281 at post-shock, and then the flow continues to slow down at the exit to a Mach number of about 0.4. And that tells us that this shape here is not acting like a nozzle. We are subsonic flow, and that the flow will continue to slow down until we exit at a Mach number of 0.4. With that Mach number of 0.4, we can take that again into table 18. And we could calculate the pressure at the exit, which again is what we're asking to do for this problem. So back into table 18, there's our Mach number of 0.4. And this time we're interested in our pressure ratio of just under 0.9, so 0.8956 is our pressure ratio. So static pressure to stagnation pressure ratio. So the static pressure at our exit is just about 90% of the stagnation pressure at state B. We know the stagnation pressure at B to be about 33.384 psi. So then our exit pressure at the exit is to 29.90 psi, and that's the answer to our question as we went through here. Now we went through and we calculated a couple little extra things along the way, like the temperatures weren't needed. I did those to show you what happens to the temperature, the static temperature across the shock, and it goes up, right? So the energy gets transferred and lost in your reversibilities, right? That creates kind of like a friction that's occurring, and that's really the cause of the rise of static temperature in our flow, as well as the drop in velocity across the shock. We could do one more thing just to confirm what we learned. So if we look at the throat with our imaginary throat of B, we know that throat has a Mach number of 1, and from table 18, we can look at the ratio or the pressure, the ratio of static pressure between the throat and stagnation pressure. So if we can also denote that that stagnation pressure is the same whether it's at the throat, at B, or E, because all of these flows are isentropic, right? So it's all one value of about 33 and some change. So we go in here and we know at the throat the Mach number is 1. And so we can see that our pressure ratio is 0.58 or 0.5283. So that ratio of static pressure is about 52% or 53% of the stagnation pressure at the exit. We know the stagnation pressure at the exit, again, is the stagnation pressure in the flow, 33.384. And so we can do that calculation, and we can get the pressure at the throat, the static pressure at the throat is going to be equal to 17.63 psi. So that's the static pressure right here. So it's about 17 or 18 psi right here, almost 30 psi at the exit. And we could compare these two pressures like we talked about last lesson. And that has to do with our converging diverging nozzle discussion. So let's go back and just review this slide from last lesson as we pull this video together. And remember, we said if we had a converging nozzle, whether it's subsonic or sonic, right, because for a converging nozzle, the highest Mach number you can get is 1. We can compare the back pressure to the stagnation pressure. All right, and so here's our converging diverging nozzle, and we want to compare the back pressure right here to the stagnation pressure through the flow. And remember, without a shock, if we assume no shock, that stagnation pressure is the same throughout the entire flow. What we're interested really is this converging diverging nozzle situation that we have here, where now we're going to compare the back pressure to the static pressure at the throat itself. So for this full converging diverging nozzle, we want to compare the back pressure to the static pressure at the throat, so here versus the back pressure, and that's what we've done on this last slide. Is we know that the static pressure is almost 18 psi here, and then the back pressure or exit pressure is about 30 psi. And we can have this relationship. We know if the static pressure at the throat is less than the back pressure, so this is an adverse pressure gradient, kind of like going uphill, the flow is going to slow down. There's more pressure at the exit than at the inlet, so the flow is going to want to slow down. More molecules will be pushing to the left than to the right, and that'll apply a force essentially on the flow to slow it down. If the pressure here is more than the exit, then the flow will continue to accelerate, and that's when we'll get that diverging nozzle effect and will become supersonic. So we could see here that our the pressure at the throat is less than the exit pressure. So we are at condition 1, we are a subsonic flow. That back pressure we just denote as where the exit is. We called it state E, right? And we just compare those two pressures. We can see that the pressure at the throat is less, so we have a subsonic flow, and that matches what our Mach numbers are. So we have Mach number at 1, and then we start to slow down, and we continue to slow down. So this really is now acting like a diffuser. So post-shock, our flow is acting like a diffuser from state B to E. So we're at a 0.6281, and then we slow down even further to a 0.4 Mach number. That's a nice thing to kind of pulls it all together. The pressures really determine how the flow behaves in the nozzle or diffuser. So big conclusion there, we're a subsonic diffuser for us. So again, this is kind of just pulls it all together. This is all of the calculations we made, and we did a lot of work in about 33 minutes or so. So congratulations. I recommend you work through this problem on your own and then watch the video again. Make sure you can do the solution. This will be a great help to your compressible flow homework and to help you on upcoming exams. If you have any questions, again, as always, don't feel, reach out to your instructor, and we'll help you out with some AI. And so thanks for the great lesson, and we will see you soon.